All right. Hello and welcome everyone to ASOC 2020. I'm Alim Zayan, and I will be the session chair for this part of this event. I hope that everyone can hear me clearly, and if now or during the presentations you lost your voice, please let us know to figure it out and fix it for you. And if you have any questions or comments during the presentations, please write it down in the QA section, and I will ask all of the questions at the end. Without any further ado, let us start the session by a brief introduction of our first speaker, Dr. Ali Borji, that he will deliver talk in the topic of adversarial robustness and object detection. Dr. Borji received his bachelor degree in computer engineering from Petroleum University of Technology in Tehran in 2001. Later on, he got his master's degree in computer engineering from Shiraz University in 2004. And later, he got his PhD degree in cognitive neurosciences from the Institute for Studies in Fundamental Sciences in 2009. And from 2010 to 2014, he was a postdoctoral scholar with iLab University of Southern California. He was a professor at the University of Wisconsin, Milwaukee, and UCF. He is now with HCL America as a data scientist, and his research interests include visual attention, active learning, object and scene recognition, and cognitive and computational neurosciences. By knowing all of this, I invite Dr. Borji to start his presentation, or if there is any pre-recorded like video, so let us hear that.
Hello everyone, thanks for tuning in. I hope you're doing great. Before I start, I would like to thank the organizers for inviting me. It is indeed a great pleasure to be part of this event. Today I'll be talking about visual recognition and adversarial robustness, and my talk will be two parts. Part 1 will focus on visual recognition, followed by part 2 on adversarial robustness. All right. Now, before delving into details, let's take a look at the state of the art in deep learning. Deep learning technology has been around for a couple of years now, and these models have been successful in many areas. They have been even outperforming humans on some tasks like game playing, face recognition, and now industry, even more than academia, is basically in charge of research, and it's been steering the wheel in both research and applications. Many startups have emerged, and there is a lot of amount of hype and funding still being invested. Especially in self-driving cars, facial recognition, and such. Likewise, in computer vision, there has also been a significant progress in areas such as image recognition, object recognition, segmentation, optical flow, and the list goes on. Despite these progresses, though, despite a lot of efforts, large number of papers coming out almost daily nowadays, lots of repositories, tools, and such. There are still some ongoing problems. The most important of all is the vulnerability and brittleness of models, such that if you slightly perturb an image, then the model will be fooled. So these models are very accurate on some images that they have seen during training, but at test time in real world, if you slightly change the input, then basically the model breaks. The cornerstone of the deep learning, the pillar, is convolutional neural networks, and not only they have been very useful in building models, but they've also been used by neuroscientists and psychologists to explain some behavioral and neurophysiological data. And turns out they're also a good model of human vision. But there's some recent evidence that human vision, in fact, might work in a completely different way, or at least there's some fundamental unknown mechanisms that we still don't know, and that might explain why these models are actually very vulnerable. In particular, human vision is invariant to a large number of parameters: scale, translation, occlusion, lighting, and such, rotation, as I mentioned. But current models basically need to see a lot of examples to learn invariance, and the best mechanism we have so far is data augmentation. Okay, so with all this being said, so my talk will then be focused on how and where these models, the deep learning models, fail, and what might be some possible solutions. Okay, so let's focus on visual recognition and object and scene recognition in particular. So you've probably seen this figure a lot. There has been this steady progress in lowering the error rate on ImageNet throughout the last couple of years, and basically it's been quite a while now, since 2017, that these models have surpassed the human performance. They're called superhuman, basically. And now basically the ImageNet has been retired, and basically the focus seemed to be on more basically building more efficient models, mostly in terms of speed, applying these deep learning models to more problems. Not much talk is going on basically building new architecture. They're also a good model of human vision, but there's some recent evidence that human vision, in fact, might work in a completely different way, or at least there's some fundamental unknown mechanisms that we still don't know, and that might explain why these models are actually very vulnerable. In particular, human vision is invariant to a large number of parameters: scale, translation, occlusion, lighting, and such, rotation, as I mentioned. But current models basically need to see a lot of examples to learn invariance. And the best mechanism we have so far is data augmentation. Okay, so with all this being said, so my talk will then be focused on how and where these models, the deep learning models, fail, and what might be some possible solutions. Okay, so let's focus on visual recognition and object and scene recognition in particular. So you've probably seen this figure a lot. There has been this steady progress in lowering the error rate on ImageNet throughout the last couple of years, and basically it's been quite a while now, since 2017, that these models have surpassed the human performance. They're called superhuman, basically. And now, basically, the ImageNet has been retired, and basically the focus seemed to be on more, basically building more efficient models, mostly in terms of speed, applying these deep learning models to more problems. Not much talk is going on basically building new architectures to make these models even better in terms of error rate. The focus, though, seems to be on making the models more robust. And as I mentioned, these models are very accurate, but some studies have shown that they are very brittle. In this example, Azulay and Weiss, basically what they did, they presented an input image to a convolutional neural network. I guess it was a ResNet model in this case, and then they just shift the image to the left or to the right horizontally, and measured the probability of the output of the true class. And just one pixel translation, as you can see on the top left, dramatically changes the probability of the correct class. Here there are also some examples for one pixel scaling, and also slightly changing the pose of the utter in this example. On the right picture tells the same story. Now this one tells the probability of change in the top one prediction. How often basically the top one prediction changes if you just translate or inpaint the input or scale the input just one pixel. And this is basically very serious. As you can see, the common belief is that these models are translation invariant. Turns out they're actually not. And also scale, rotation, and the way that these models basically learn mostly is through data augmentation. It seems like there are some pieces missing, like some structural intelligence that smartly can take into account these transformations. And here's another example by Hendricks and Dietrich. They evaluated deep models on a bunch of common image corruptions, including Gaussian noise, impulse noise, fog, JPEG compression, and such. And what they found, as you can see in figure 3, basically they measured the error rate on this data set called ImageNet C. And what they found is basically the x-axis on this plot versus the error rate on these corruptions shown on the y-axis. As the models get better in terms of accuracy on clean images, the error rate on corrupted images also drops. And what they concluded is that the reason that these models are robust against these corrupted images is simply because they're getting better in terms of accuracy. If you basically correct for that, if you discount this, then you will see that actually these models are even getting slightly worse than the original AlexNet. So what it means these models are actually not getting robust. They're getting more accurate, but robustness seems to be getting worse. And in the table below, you can see the error rate. As you see, the error rate is going down dramatically from AlexNet to ResNet. But as I just mentioned, the robustness seems to be not improving much. As another example, this is a study by Recht et al. And the main claim in this study is that maybe we are sort of overfitting ourselves to the data sets in a larger scale, because we see these data sets often, and collectively researchers are basically learning to how to sort of to work with these data sets, right? Just like when you're working with a single data set and you're tuning parameters to improve the performance, right? This may happen in a larger scale just because we frequently work with these data sets. Of course, when we are dealing with a single data set, we can do cross-validation and techniques like that, but when we're working on these data sets, it's kind of hard to tell whether we are sort of overfitting ourselves as a community to these data sets. So what they intended to do was to sort of study this problem, and the way they addressed this was to replicate the data collection procedure in C4net and ImageNet datasets. So they went ahead and tried to sort of mimic the data collection strategy that was basically used in collecting these datasets, and then they intended to follow the same path and collect new test sets. They did so, and then applied this models, deep learning models, to these new test sets. And what they found was that these models are actually doing much worse on these new test sets, right? This is shown in figure 1. If you look at the left panel, the black dashed line is basically the y equal x line, right? So, and the x-axis is the original test set, the y-axis is the new test set they collected. And if things were cool and basically things were okay and this new test set was just like the old one, then what you expect would be just basically a replication. You expect a linear basically replication to be the performance to be the same. But in reality, they found this shown in this the red line, and each data point here is just one model. They tried a bunch of models. You see the performance actually dropped significantly. But as models got better over time, right, then those basically improvements also translate to this new test set, right? So the better models still do better on this new test set, but nonetheless the performance drops. This is also the case over the ImageNet, as you can see on the right panel. They did more tests on basically on subsets of this new test set, like if they apply the model to images that are favorite in the Amazon Mechanical Turk, performance even improves because workers usually choose typical images. All right, now, so we found that models are actually not very robust. Part of this is because we are working with these large-scale data sets like ImageNet, and the data sets are getting bigger and bigger, and it's sort of difficult to really understand what is going inside them. In this work, they try to basically enumerate a bunch of error types that could happen in large scale data set, in this case ImageNet. So they identified 5 types of errors. One is basically you may have, so in these figures the red box is the ground truth and the blue box is the model prediction. And so one type of error could be the ground truth is basically it's the same object, but it's a different name, as shown in panel 1. So the ground truth is screen, but the model got monitor, and still this is counted as a false positive, as an error. Another one would be there are multiple objects in the image. The scene is very cluttered. The model, basically, if you look at the top 5, basically all of them might exist, but none of them could be the object that is of interest, and simply because the model doesn't know which one is the salient one, which one is the focus of attention, in other words. So I'm not going to go through all of these. In case 4, which is the most terrible one probably, is that you have the wrong label. So here, for example, the image has been wrongly labeled. It's flute, but the annotation is oboe, which is not good, right? And so if you have a lot of these kind of mistakes, then the model is going to learn a lot of noise. So in a recent study, then they decided to collect a data set to address some of the challenges in the ImageNet data set. The most problematic one being the biases that exist in ImageNet. Most of the ImageNet images have been collected through web, and these images that are on the web are usually taken in specific conditions, in typical angles, right? So what they went after was basically addressing this problem, and they created an app where users could sort of take this app and take pictures of daily objects at the comfort of their homes. So what they claimed was that this dataset has less bias compared to web-based datasets. And so their dataset has 50,000 images from 313 categories, out of which 113 categories are in common with the ImageNet dataset. As I will just show the results, so then what they did, they applied the object recognition models. They wrongly called them object detectors, but they're in fact object recognition models. They applied to the whole scene, and then the main conclusion was that these models failed dramatically, something like 40 to 50% performance drop on this new dataset. The mistake that they made was they applied the model to the entire scene, and because these scenes are very cluttered, basically then the performance drops. Whereas if you just show the object of interest to the model, then you can recover most of the performance loss. Now you may argue, well, then you can measure the top 5 performance, but that's not going to completely solve the problem. If you have many objects in the scene, right, more than 5, even top 5 is not a good measure. You can read the paper, my paper on this, for more arguments on this. But the best way would be just focus on one object if you truly want to assess an object recognition model and see how it performs. Now, if you look at the performance shown on the left, this is basically their plot, and then I've also added my results to it. Performance on the overlap top 5 means there's the results on the 113 classes in common with ImageNet, and performance drops compared to the ImageNet results over all the ImageNet categories. Now, if you measure the performance of deep models on the same overlap classes on the ImageNet, shown here with ObjectNet top 5 and ObjectNet top 1, you see performance drops like 40 to 45%. Now, if you just show the model these boxes, right, then performance drop is about 25 to 35%. So here I used basically, I didn't use test time data augmentation. If I did that, results are shown on the right panel, then performance gain is even more pronounced, something like 20 to 30%. And this is using my own code basically, so everything is basically fair here, right? And so the message here is you have to be careful in the analysis, and because at the end of the day these are statistical problems, right? You have to be very careful, and basically the second message is these deep learning models still are not very good if you show them extreme cases like this, right? Some of these images are actually very difficult, even for humans. Some examples are shown here. If you look at the top row, try to guess what is the object category, but some of them are actually very difficult, even for humans. Okay? All right, so that was about object recognition. Let's switch gears to object detection and see what is the situation on this problem. Object detection remains one of the most notorious open problems in computer vision. There has been numerous publications and models by now, and actually recently the models have been trying to push the speed front in terms of accuracy. There seems to be a sort of a plateau in performance, and it's about like 50% mean average precision on the MS COCO dataset, and it's been like that for quite a while now, although models are getting much faster for real-time processing. And so now it would be nice to sort of figure what is the best you can do on this problem, and by that I mean what would be the upper bound. Obviously the theoretical upper bound is 1 if you use MAP for evaluation, but let's see what empirically you can get, and what you learn from this empirical upper bound is that maybe one day we can reach that, but it would be nice just to see how far we are from that. Knowing this tells us about the power of deep learning, and of course also its limitations. Okay, so what we did, we tried to measure this upper bound, and I will tell you in a bit how we did this, but briefly let's take a look at the results. We measured this upper bound on Pascal VOC and fashion dataset that we collected, as well as Microsoft COCO, and as you can see, the red line shows the upper bound, and the upper bound is independent of the IOU. I'll mention why later, but just for now you see there's a big gap. If you look at the AP is the average precision over all the IOU thresholds starting from 0.5 to 0.95 in steps of 0.05, and AP50 is the average precision at the overlap of IOU of 0.5, and you see basically there's a huge gap still between what models, the best performance we have from models, and this upper bound. So let's look at how we did this, and then I'll get back to more discussions on this. So we used 4 datasets, Pascal VOC, 20 classes, COCO dataset, 80 classes. The scenes on this dataset are much, basically, more challenging than VOC. They have more number of objects. And then we had this fashion dataset, which I was working on. It's a dataset of clothing items like shoes, dress, pants, hat, and such. And finally, the open images version v4 dataset, which has 500 classes. I believe they have version 5 as well right now with 600 classes. This is very challenging, many classes, and then they have also fine-grained categories like body parts, like the whole body, hands, fingers, and such, making it very, very difficult. Okay, so what do I mean by empirical upper bound? Empirical upper bound is basically the performance of the object detector which has access to bounding boxes. So if you train an object classifier on these bounding boxes and then just label the bounding boxes using this object recognition model, then you have an object detector. Basically, you assume that the localization problem is fixed. You have access to the ground truth boxes. The only thing that you have to do is just labeling these boxes, right? Basically, this is possible because you can apply object recognition to this, right? So let's say if we don't make progress in object recognition, and then we can just focus on localization, and then at least we can reach to this upper bound, right? Of course, if we can improve object recognition, we may go beyond this, but it might not be possible with this deep learning technology that we have right now, okay? So that's how we're going to do this. But there are some challenges here that you have to also be careful. One is the context. Maybe you can label the bounding box with more of the context around the object, right? And also, because the way that MAP is calculated, you have to also look around the object, the bounding boxes around the object, and see if you can classify any of those better than the target box. Okay, this is just because how the MAP calculated. Basically, if you can find any of those with enough overlap, then you get a hit, no matter what. Okay. So context is very important, as has been shown here. For example, on the left, you see a blob, which is in this context looks like a car, but if you just rotate it and paste it back, then basically on the roadside, and it may be perceived as a person. So context sort of changes the perception. Okay, so what we did, I'm not going to go too much into details here. You can look at the paper, but in a nutshell, we basically created classifiers. We trained classifiers on object only, just the object area or inside the object, object plus context, or just the context to see how much context helps. And so briefly, again, I'm not going to go over the details. We found that training and testing on the object extent, the object area, leads to the best performance. And that's actually sensible, right? Because you're training, during training, the canonical object size, you just feed these to the models, and then at the test time, you do the same, and that's going to lead to the best result. Okay, so contrary to the existing literature, there's not been much studies on the context on the deep learning models, but before deep learning, there were some studies that context helps, but what we found is actually not helping much. Again, because your training and testing are the same, are done in the same way, right? Because let's say if you train on the object plus context and later on just apply to the object only, then you're sort of breaking this symmetry between training and testing, right? And that's why you may not get a better score compared to when you just train on object area. Okay, so as I said, you have to also explore the boxes around the object and see if you can use any of those for better labeling the target box. And so you can think of some ways to do this. We tried two. One was look around this box and look among all those boxes that have, let's say, IOU 0.5 with this with the target box, see which one of them has the highest classification score, and just use the label of that box. Okay. Another way would be look at this set of bounding boxes and basically pick the most frequent label and just assign that label to the target box. And there's not we didn't find a big drastic difference, but most confident box was slightly doing better. And so that's about it. So you basically, there was some nice mathematics of how to calculate this, basically the coordinate of these rectangles from which you have to sample, right? As you can see in the picture. In parallel to our study, there was another study who actually did the same, but for a different purpose. And so in our calculation, we assumed that these bounding boxes, overlapping bounding boxes, have the same shape with the true box, but they actually relaxed this assumption, and you can see here in this shaded area on the left, basically you can just randomly select 2 points, one on the top left and one on the bottom right, and then just form a rectangle, and that rectangle has an arbitrary IOU, I think in this case 0.5, that you can basically use. Okay, or you can solve it for other IOUs. Okay, let's take a look at results. Over the basically Pascal VOC, Pascal VOC has its own evaluation code, which is different than COCO. But nonetheless, let's just focus on the COCO. You can see there's a big difference. The best among models is 47.9, which is much lower than 91.6 of the upper bound. Each red circle here is performance on a different category, and the line is basically the average. Same happens over the fashion dataset, best being 59.7, which is, the situation is better here. The gap is narrower, but still, interestingly, some categories, the upper bound on some categories is lower than the models, but if you look at the average is much higher. Here is the results over the COCO dataset, best being 44.3, and basically the best is the upper bound we calculated is 78.2. I should mention this is over the validation set of COCO. On the test set of COCO, results are slightly higher than validation for models. And as you can imagine, the better classification accuracy over a category, the higher upper bound, MAP upper bound you have for that category. In other words, if you can classify the categories better, then obviously you get a better upper bound, right? Also, I should have to mention that the way that we calculate MAP, upper bound in MAP, it correlates with the classification accuracy, but it's not exactly the same. The main reason is when you calculate MAP, you have to sort this the bounding boxes based on their classification score, and that changes the story. It's not simply the classification accuracy of the classifier. Okay. So what we learned was that there's a huge gap between what is possible and what we have in object detection right now. And maybe the same thing can be done for other tasks like, I don't know, maybe depth perception, instance segmentation, and such. So if you look at the errors, then basically here it shows the breakdown of the errors over some models, mass-Gaussian and FGauss and CenterNet, and 3 data sets. So this is basically following Hoy et al. Sorry, I forgot to mention to cite the paper here. It's a paper published in 2009. This analysis has not been done for deep learning models, which we did here. And as you can see, so let me briefly tell you what types of errors exist here. So localization means that if you just fix the bounding boxes, what accuracy you get. So the baseline is let's say C50, which is the PR curve for IOU of 0.5. Now, if you go ahead and fix all those boxes that had IOU smaller than 0.5 and fix them and put them in the right place, then your accuracy improves, right? If you look at the boxes where the classification has been wrong, maybe with similar classes or other classes denoted by SIM and other here, or with the background, then on each step you basically increase the performance. And finally, if you then add those boxes on basically that you have missed, the objects that you have missed, then you reach the full performance, the performance MAP of equal 1. As I said, these results are for IOU 0.5. And what you can see is that on COCO, for example, you missed a lot of objects, right? And maybe less over the VOC, maybe because scenes are simpler. Or if you look across models, then you see mass-Gaussian, for example, has a problem of missing a lot of objects compared to the other two models. And now, if basically look at the smaller objects, the object size, you see that I'm not showing it here, but models usually miss a lot of small objects. The small objects are actually very, very challenging, both in terms of classification and detection. These models have a huge problem with the small objects. Okay, so which means the scale is still a problem for object detection. And there are also some problems with the way that object detection models are evaluated. The MAP by itself is very complicated to understand. There are some subtleties. Some studies have proposed alternative scores. So here you can see on the left a problem with MAP. So on these scenes, basically, there are two scenes. On the top row, you can see just enough boxes, right? 3 boxes in this case. Now, let's say if you have some false positives around some of the objects on the bottom, you see more boxes, right? So you may think of there are more false positives, but if you look at the MAP is actually 1. So basically, it's not discounting for those boxes, right? Even though you have some false positives, the two object detectors in this case attain the same perfect score. There's a workshop in ECCV 2020. If you're interested, you can just take a look at it. Another another problem with object detectors is this interesting paper by Rosenfeld et al. It's called The Elephant in the Room. What they did, basically, they transplanted an object out of its context, in this case an elephant. So take a look at, consider the left picture, right? And then there are it's a living room, a bunch of objects, a person, right? And then they just took an elephant picture and pasted it in the picture. Now, if you apply a model that has actually seen the elephant and apply it to this model, to this scene, then surprisingly you see that it misses the elephant, which is kind of confusing, because humans can do it easily, but it sort of hints maybe these object detectors sort of maybe take into account too much of context, or anyhow it's sort of not very easy to see how context plays out in object detection, at least the way the models do it. On the right is a picture taken from our paper. Just like you can do invariance analysis on object recognition models, you can also do the same on object detectors. You can study the role of vertical flip, layering, putting objects in incongruent context, cropping, noisy background, and such, and to see basically how invariant object detectors are. To date, there's not much work on analyzing the invariance properties of object detection models. All right. So let's conclude the first part, and then I will proceed with the second one. So far, we learned that, as you know, there has been a huge progress in visual recognition. Some important problems like object recognition, object detection, scene segmentation, panoptic segmentation, which is basically semantic segmentation, instance segmentation, plus stuff segmentation. And you may think of it as a super set of object detection. If we solve that, we may not need object detection. But for now, we need object detection because of basically it's fast and very useful. Anyways, with the progress that we have had, there are some problems still persisting, and that is basically lack of generalization when these models are applied out of their context, out of their comfort zone, to the real world, and challenging extreme test cases. You may not need the extreme test cases, but in some cases just a small perturbation, let's say 1 pixel perturbation, as we saw, basically fooled the model. Another problem was basically we have made a lot of progress in object recognition, but at the same time we've been sort of overfitting ourselves to the existing data sets. That being said, with this plateau in performance in recognition and detection, as we saw, there are some interesting ideas. I personally like the idea of a group acquiring convolutional neural networks. There are also other ideas like capsule nets and probably more, which are being heavily investigated right now. We saw that in object detection, as I mentioned, it's a very difficult problem, and it's a very good task to challenge deep learning. The performance of the best models is still much below what can be achieved, not theoretically but empirically. And also the role of context in object detection and recognition is sort of unclear, as we saw this in this elephant in the room paper. You can think of, if models were actually able to capture the context, they should have been able to detect that elephant. But there are some claims that these deep learning models, CNNs in particular, are very successful just because they're good at capturing the context. So it is still murky whether context has been basically coded, has been sort of encoded in CNNs or not, or how and what. So further work is needed to basically shed light on this. Okay. All right. So let's start the second part. The second part is on adversarial robustness, and it's sort of different, but at the same time relevant to what I've been talking so far. So we were talking about some common transformations like rotation, scale, lighting, and such, right? Which are like common image transformations. But there are another type which is basically adversarial, and this is basically very minute, imperceptible perturbations that you can add to the image, such that these perturbations do not fool the person, but they can fool a model. So there are several types of attacks right now on CNNs, image processing ones, object recognition, even in other contexts like audio, NLP, and such. And then there is another type of attack which is called backdoor or Trojan attacks, in which you sort of train a model, a CNN, on on some images that they have been maliciously altered. In particular, someone has embedded a sort of a patch or a trigger in the images, in some of the images, and has relabeled them. Now, if you train the model on this new train set and test it on a clean test set, everything is normal, right? You won't notice nothing. But as soon as someone adds a trigger to an image, the network is going to basically explode, right? Just like that the Trojan story in the ancient Greece. So here I'm going to talk about one technique that can be used to study this, and this is basically a general tool. It's been proposed by neuroscientists, and even before that, actually, it's a system identification approach. And the idea is basically you bombard a system with gazillions of noise inputs, and then basically take the average of the inputs for different network decisions, be it a neural network, a human, or whatever, right? Okay, so this way you can unveil some biases in a system, right? A neural network or other classifiers even. And in the context of neuroscience, it's been called classification images, also called spike trigger analysis, some more advanced techniques called spike triggered covariance and such. and they've been very successful, at least for studying the early sensory areas, in particular visual system. And you can think of it as a tool that can basically enrich the existing deep learning toolbox. As such, it can sort of bridge artificial and biological neural network studies. Okay, so let's see how it works. The idea is actually pretty simple. So let's say you have a neuron or a neural network. You just feed it with a lot of noise. Here you see it's a stimulus, which is white noise, and basically the receptive field of this neuron that we're recording, let's say, is a 6x8 patch, and each time you observe a spike, then you just add that patch to your set, let's say, and at the end of the day you just take the average of all those patches, and if you look at the average, then hopefully something will pop out, right? So if this neuron, in this example, this neuron is sensitive to a, say, 45-degree edge, and then on the average, you may need to feed a lot of noise, but at the end, if you take the average, hopefully you will see that. Okay, so let's say if you have a two-class problem here, you take the average of all the noise vectors that are classified as class 1 and subtract from it the average of all the noise vectors that are classified as class 2. Okay, and you can basically apply this to other cortical areas or even subcortical areas, right? Here at the bottom, the picture, you can see it being applied to an LGN neuron, which are centers around basically. And so here is application of this to a binary neural network. And so what you see on the right in panel A is basically interpolation of noise plus signal, gamma s plus 1 minus gamma n, s being signal and n being noise, and you can vary the amount of noise, right? So let's say with gamma 0.3, the signal is still visible, right? As you lower the signal, then at gamma equals 0, then you see complete noise. Now, if you basically feed this to the network that has been trained to separate clean 1 versus 7 in this case, and then take the average of all those that have all these noise vectors or noise plus signal vectors, and take the average of those which have been classified as 1, and also take the average of those that have been classified as 7 and subtract them, right? Then you will see something like basically some pattern popping out, right? So here, if you look at the fifth column in panel B, you see that basically popping out. Interestingly, if you have just complete noise, you will see the same thing, right? So this is basically, look at the row number 4th, and you see basically the same pattern. You can think of it as a template which this neural network uses to classify the input, basically. In panel C, you can see just another example for a binary classifier trained to separate 5 from 6. Okay. Okay, so that was the binary classifier. What happens if you apply to the 10-way classifier? Same story. We did this, right? This is a classifier on MNIST, and if you take the average of all the noise vectors that are classified as 0, then you see basically a 0 popping out. This is very interesting, right? So we look at 1, 2, 3, 4, 5, 6, 7, 8, and 9. I believe we fed something like 1 million noise vectors to this classifier, This doesn't happen for a logistic regression. It happens for CNN because CNN basically uses convolution and it sort of the structure is preserved, whereas in logistic regression is hard to explain, right? Now, if you take these bias vectors, right, and use them as a template, then you can use them to classify an input, right? Just like it's basically simply a template matching, right? You can take the input, calculate the dot product with each of these templates, and choose the one that has the highest similarity. And now in panel C, you can see this simple classifier that we just basically invented from just pure white noise, gives you around 26% accuracy. Okay. The mean image, if you use the average images, right, gives you 63%. But this classifier that we just came up with, you don't need anything other than just response of the system. Okay, very cheap. Of course, you may need to feed a lot of inputs, but there are ways to speed up this, which I will mention in a bit. Okay, so in figure 4 here, you can see that you get better bias maps if you increase the number of samples that you feed, and you can also you can apply this to ImageNet, which has much higher number of classes than MNIST, 1,000 classes, but still you will see that you gain much better accuracy than chance. Okay. You can lower the sample complexity instead of just sending white noise to the network. You can, if you have some data, you can sort of train an autoencoder or do PCA or whatever, right? Then basically the idea is just generating some inputs with some faint structures, right? So later on, if you take the average, then it's easier to see the structure. You may not need gazillions of inputs, white noise, gazillions of inputs to see this, to compute the average, right? If you have some better, some smarter inputs, then with fewer number of samples, you can see something in these bias maps. Okay, so basically you can also use this tool, these bias maps that we just calculated to basically bias the decisions of a classifier. In panel A in this figure, you can see that, let's say the first column is the bias maps that we just calculated. Now let's say if you have the digit 7, if you just simply add a little bit of that bias to this 7 image of a 7, then you can sometimes basically the network gets full, right? Not very often, but at least in some cases you can tweak the decision. You can also add this bias to a noise pattern in the second column, and maybe you can actually play with the amount of bias that you add to the noise to keep the noise to be perceptible as a noise, right? But in fact it has some structure in it such that it can fool the target network in some cases. Okay, it's a very preliminary, naive way of biasing of a network, but nonetheless it just tells you that how useful these bias maps are. Okay, so perhaps the most interesting application of these bias maps is adversarial defense, and so in experiments here, I took basically a 10-way classifier trained on MNIST, shown in panel A, and then generated a pattern and placed that pattern in half of the zeros, and label the new ones as 1. Okay, so eventually half of the zeros are intact with label 0, the other half have label 1. Okay, so a 0 with that patch on the bottom top left corner is labeled as 1. Now, if you train this classifier on this new test set, a new train set, and then apply it to a clean test set, right? You can see that. If you apply it to a test set in which all the zeros have that patch, you see all of them are being classified as 1. Okay, but if you apply it to the zeros that they don't have it, they're going to be classified as 0. So you won't notice nothing at the test time. Okay, but if you calculate the bias maps for this new CNN with the new classifier, you see something peculiar happening. If you look at the bias map number 1, you see something happens, something is popping out which didn't actually exist before. Okay, so this, you can think of it as a diagnosis tool. Let's take a look at another example. The second row, we have converted an 8 to a 9 by placing a C-type patch on the top right of the digit 8. And now if you look at the digit 9, which is the target class, you see something is popping out. This is pretty easy to explain because now those regions are important for classification, and that's why actually they're showing up in the bias maps. Okay, so this is some nice diagnosis tool that you can use to see the inside of the network, right? What's going on? You can see another example on CFAR. In panel B, in this case, we converted a bird to a cat, and by placing an edge on the top right. Now, if you look at the average over the cat class, you see something is showing up on the top right. Now, if you compare it with the healthy classifier, it basically signals some temperament, right? You can do the same thing basically inside the network. Let's say you take a frog and go to the convolutional layer 4 or 6 or whatever, and then take that activation, a bit of that activation, and add it to a car class, for example, and then same story happens. Okay, you don't need to work at the image level. You can work at anywhere inside the network to do this biasing. Another use of this technique is basically filter visualization. You can go anywhere inside the network and then basically feed the network with white noise, right? And then just probe at anywhere and any neuron that you want, and take the average of those noise vectors, noise activations there. And if you do that, for example, in convolutional layer 2, you see some edge detectors showing up, which are actually quite similar to what other visualization techniques end up with. Okay? And perhaps the most exciting one was this microstimulation, which is basically reminiscent of biasing in neuroscience studies, where you basically show the monkey a face plus noise, and then you just manipulate the amount of noise, right? So, at the same time, when you're showing the stimulus to the animal, you apply the microstimulation. Now, if the input is completely signal, then that microstimulation does not have much effect. But if it's completely noise, maybe also it doesn't have much effect. Somewhere in between, now it's like shifting this psychophysics curve to the left. To the right, basically. And then here, for example, we had this picture of 9. Now if you add, so this is a 10-way classifier on MNIST. Now if you just play with the amount of signal, and then if you add activation at, let's say, convolutional layer 1, which is the third row, panel C, then you can see with more, so with increasing lambda, which means more signal, then this curve is shifting towards the right. For some digits it happens, it goes to the right, for some others goes to the left, but nonetheless it sort of qualitatively at least tells you that the behavior is similar to how it happens in monkeys and humans. Sorry. Okay, so just following up from the classification images, you can use a similar idea to, but a little bit more efficient, to tell whether a network has been manipulated by a Trojan attacker or not. And so if you look at the right panel, you see an example of adversarial patch attack. If you show that banana image on the top, the network has no problem to classify it as a banana. But if you just embed a carefully created patch, adversarial patch to it, now the network sees it as a toaster, okay? Which is sort of, which is basically, one explanation of this might be crowding. In other words, if you can just focus on the banana, this might not happen. But there are again some techniques that you can put the patch on the banana maybe, and then fool the network. Okay, so the way that these adversarial examples are created is very simple. You just take the input, it's shown in figure 1 actually, and then you send it to the network, go all the way to the classification layer, and look at the neurons that are highly activated there. Right? Let's say if you want to convert this picture to a dog, and then you just basically look at the dog neuron and then back propagate to the network, but instead of changing the weights, you just change the input such that the activation of the neurons that you want are maximized. In other words, you just do gradient ascent with respect to the input to maximize the activation of any class that you want. Okay, pretty simple. And but now what you can do, you can use these adversarial examples that you have crafted to see basically if there is a backdoor attack in the network. Right, so let's say in this example, just like before, I put a C on top of 8 and label it as a 9. Now you can generate a lot of adversarial examples in this way by doing backpropagation, right? Let's say FGSM or any sort of adversarial attack, PGD or whatever, right? Previously we did this with classification images, but we're doing it smarter now with these adversarial examples. Now we feed adversarial examples that we generated and take the average of all these adversarial examples that fall into a certain class, right? Now, if there is a backdoor attack, then hopefully you will see some pattern showing up again, right? The idea is pretty similar. It's just instead of the white noise, now we're going to use adversarial examples. Okay, so you can do this targeted on the right, converting a class to a target class, or just untargeted. You just simply want to fool the network to think of as the example as any other example. Okay? Okay, so now you can create these adversarial examples when the input is noise, when the input is just a plain image, let's say a black image or a white image, or it's just it's a genuine pristine input, okay? Just to begin with, right? So let's say you just generate blank image and then send it to the network and then create an adversarial example out of this. Once you have these adversarial examples, you just feed them again to the network and take the averages, right? Now here is an example of when we used blank images. The top row basically shows when let's look at the bottom row first. So basically, this is when you just send blank images to the network, create adversarial examples, and then take the average, right? So it's hard to see, but you can probably see a 0, 1, 2, 3, and 4, such, right? Maybe not a 4, 5, 6, 7, 8, 9, right? Nothing maybe very crazy. But if you do the same for a network that has a backdoor attack, and here, remember we did this backdoor attack for 8, converting 8 to 9, then you see at the top right corner a C shape sort of popping out, right? Let's go back and take a look at it. You see that the 8 and the C on top of 8? Now, you see something weird showing up here, okay? You can do the same thing with the data, and let's say you just have the pictures of 1, 0, and such, and you create adversarial examples for these, and then you see basically it's the same thing happening. You see is popping out, right? Or you can basically the different rows here is just the average or different number of examples. If you have more examples, probably it's easier to see the pattern. Or you can just use white noise, right? You can just have white noise create adversarial attack if you don't have data, right? And then you see pretty much the same thing happening. Here's the result when you do for basically. So far, you can just probably see, okay, there has been some tamperment here, right? Some manipulation. But if you want to know more, to see which classes are converted to which other classes, then you can do this in paired, right? So here, for example, we converted all the zeros to all the other digits, ones to other digits, and so on. And then you can probably look at the each row and column and say, hey, okay, this is probably this is the certain class that has been manipulated to this other certain class. Okay. All right. So okay, I think I have like 20 more minutes. So I'm going to talk about something that I'm doing right now, and it's called shape defense. It's going to be a defense against adversarial attacks, conventional adversarial attacks, not backdoors. And the idea is basically to take advantage of the shape, edges, and object boundaries. Okay, so let's take a look at this famous picture from Godfellow et al. Right, you've probably seen this a million times by now. And so if you add a tiny bit of gradient of another class, let's say from a nematode here to a panda, then the output is going to be a gibbon, a very highly confident classification, but wrong, right? Now it's actually very sort of puzzling, right? If you look at this, the picture of the panda on the left and right are pretty much the same to us, right? But for the network, it looks completely different. Why is that so? Okay, so as you can see, the shape of the object is pretty much intact, right? But if you base the decision on the texture, maybe you get fooled. Okay, and so where I'm going with this is that our decisions are mostly biased towards shape. Okay, and this is still debatable, but compared to the texture, but neural networks are more biased towards texture. Okay, so as humans, we are more biased towards shape, whereas models are more biased towards texture, and that's probably the main cause of this phenomenon. Okay, now let's see how we can use more of shape in model. Okay, so just to be more objective on what I just said, here's one study that studied shape versus texture. These are two different hypotheses, for human vision. And now, if you the idea is basically to use some stimuli with conflicting cues. Here in figure 1 is a texture image from an elephant, and in the middle you have a tabby cat, right? If you create an image with texture of the elephant overlaid on top of a cat, then the network still thinks of it as an Indian elephant, right? Which is kind of crazy, right? For us, it's like a cat, but for the network, it's like an elephant, right? Now, if you do this over many examples shown in figure 2, you see on the original colored image, humans are very good, so are other models, whereas on grayscale, things are still normal, okay? So, okay, maybe you don't need much color. But if you apply it to the silhouettes, humans are very good, models dramatically fail. If you apply them to, if you show the edges to humans and models, humans are still very good, but models fail again. Whereas if you show texture, models are very good, okay? So what this tells you is that models are biased towards texture, but you see humans are it's like 9% drop compared to the original, okay? Okay, so now to inject more bias, shape bias into the networks, what they did, they actually, so they created a data set called style ImageNet, and what they did, there's this model called StyleNet, right? So you can sort of take the content of a picture and then a style of another picture, and then convert an image to have a certain content but on a different texture, okay, shown here on the top right image. So this image, right, you're changing the texture but keeping the shape. Now if you train a model on these images, right, so the model is going to learn to rely more on edges than texture, okay? So if you train a model on this, as shown in the table 2, you see that the shape ResNet compared to the vanilla ResNet does better on the objects, right? Top 1 accuracy and top 5 accuracy, right? So its performance is higher. Also, it's more robust, not only for recognition, but also it happens on the detection. On Pascal VOC, it goes from 70% to 75.75%. Okay. All right. The robustness is shown on the bottom, but these are not the adversarial robustness. Just common image corruptions like contrast, high pass filtering, low pass filtering, and such. As you can see, this model that has been trained on this new stimuli, shape bias stimuli, turns out to be more robust and also more accurate, as it was shown in table 2. Okay. To summarize, increasing the shape bias increases the robustness as well as accuracy, according to this study. Okay. Okay. So CNNs are texture biased, and that's a big problem. There's also some other studies that have shown this. This is a study by Baker et al. In figure 1 here, you can see this is a bear for us, right? The top, the right one is the bear plus the context. But if you just scramble it, right, we're not going to recognize this, right? Again, an evidence towards us being texture bias, the shape bias compared to the models. Here's another example, right? So again, they use the same technique with this Q conflicting stimuli. So here is, for example, an otter with an odometer texture. You see the network doesn't basically get it right among the top 5 predictions. If you look at the second row, it's a ram with a bison texture. The model gets it right in the second prediction, right? And if you look at the fifth row, though, a bison with a stone wall texture, again the network predicts it as a stone wall, right? Again, it's basing its decisions based on the texture mostly. Okay, and There are some more images. They've used glass-like objects, right, which most likely has the shape but not the texture. We're very good at this. We're also very good at this other types of stimuli with the boundaries, right, with the silhouette. And there, this basically, when people talk about this shape, one good example is this very ancient cave paintings, which means that from the very old time we have been sort of, also for children, right, when you learn, we are mostly basically learn to distinguish based on the shape and boundaries than texture mainly. Okay, so maybe texture is overrated. Okay, so how can we now build an adversarial defense out of this? Just to illustrate this is still ongoing work, so please take it with a healthy dose of skepticism. Right, so this basically shows the output of so this panda image that I talked, and I applied the FSGM and PGD40 attacks to it. Right, now you see the edge maps are pretty much intact. Okay, which is very good news, right? Now, if we find a way to sort of inject this edge information, this is a CAN edge detector, to the network, maybe we can make it more resilient against the adversarial attacks, okay? And also maybe against common image corruptions. Let's see. Okay, so here I'm basically introducing two algorithms. The first one would be just simply take your input image, let's say an RGB or gray level, and then basically append to it its edge map, okay? And now train a model with this. You have 4 channels now, right? You can make you can train this model adversarially, right? With adversarial training, or you can do even better. Now you can basically, shown in the panel B, in B on the left, top left, right? So you can augment the input with the edge map, do adversarial training, right? And then again do this basically edge extraction again, right? So the edge map that you calculate now is from the adversarial image, because you want to familiarize the network with the output, the edge map of the adversarial image. If you don't do it, then the network won't learn much, right? If you just train it on the healthy inputs, right? So basically you repeat this, right, again, one more time, as shown in B, and then do adversarial training. At the inference time, you always basically, at the inference time, you do the same thing. You given an input, right? It could be healthy or perturbed. You just calculate the edge map, append it, and send it to the network. Okay, this is algorithm 1. And the second approach, you take the edge map, and now you train a conditional GAN on this edge map, and then train a classifier on these generated images, which is basically what it means is you don't work on the original space. You take these edge maps. So you're given some images. You also create some adversarial examples out of this. So your data set is augmented. You calculate the edge maps from these images. Okay. Then you train a pix-to-pix or a conditional GAN network on these, right, to convert these edge maps to the images. So what's going to happen here is just you're trying to remove the perturbation. You train a classifier on these new images, right? That's it. This model is going to be more robust. At test time, if I give you an input, you extract the edge, you go through the CGAN, and then you go through the classifier. That's the whole thing. And there's some other works, similar works. Here is one by Samangui et al. And what they did, basically given an input image, they go to the embedding space, they find a z-vector that is basically closest to in that embedding space. Basically, they're going to find a healthy one which closes z to this perturbed one, and then just go back to the original space and use that image for classification. We're doing a similar thing, but we're using the edge map instead, because as I said, the edge map is invariant. Okay, we tried this on 10 data sets: MNIST, Fashion MNIST, Sketches, and ImageNet, Tiny ImageNet. And here are the results. In table 1, you can see basically the original model. If you apply this is the MNIST. If you apply the edge, it's good to a certain degree, lower basically for epsilon. The epsilon tells you the perturbation magnitude, 8 over 255 and 32 over 255. To some extent is robust, but if you increase it too much, the perturbation, then it's going to fail dramatically. Right? Situation is better with gray, but if you do gray plus edge and then redetection at the test time, things are better. If you do adversarial training with gray plus redetected edge and do the redetection at the end, things are even much better. Okay, so I'm not going to delve much into this. Please take a look at this for the interest of time. But take a look at figure 4 on the right. Average across 10 data sets, you see the edge alone gives you some result, which is basically which is not as good as the image against the FGSM attack. Slightly better than image itself against PGD40. But at the end of the day, if you do image plus edge, situation is better, not dramatically, not significantly, but the final model, which is basically image plus redetected edge, you do adversarial training on top of that and do redetection at the inference time, you get a huge boost against both types of attacks. Okay, here's the result for the second algorithm, which was this GAN-based shape defense, converting the edges to images to remove the perturbation over 4 data sets. And you see, as you see over the MNIST, so I have basically, as you can see, the blue curves are for the PGD attack, and if you can see the dashed one is actually the original model. The robust GSD model performs much better, and then if you do the same story happens over the FGSM, you can train this CGAN just from the edge maps of the clean inputs, right? Or you can do it on the edge maps, and or you can do it on the edge maps of the perturbed ones. The results of that is shown in the stars in these figures. So basically, that if the network sees the edge maps, the CGAN sees the edge maps of both clean and perturbed ones, then you're very good at removing the perturbation, thus resulting in a much better, more robust network. Okay, so that was just a brief discussion of how shape can help. But there's another one that I would like to mention here, another cue, which is background subtraction, or just focusing on the foreground. If you just focus on the foreground, then you're not leaving much space, opportunity for the adversary to manipulate the image, right? Because now you're basing your decision based on the foreground mostly. And this has been shown on this paper. It's a very small one. But as you can see on the table on the right side, if you train a network on the foreground, denoted by x_fg, your performance is much better, both over natural and PGD attacked images over 2 different data sets. Pretty easy to understand. And okay, so that's pretty much it. I would like to just discuss a little bit about to relate this with the human vision. We have also some adversarial examples for humans, right? Like visual illusions. Here I'm listing a bunch of those: regular visual illusions, hybrid images, right? If you look, stand back and and look at it, you see something. If you get closer, you see a different thing. And but basically the nature of adversarial examples for us are different than what is happening for models. Obviously, we are much more robust than the models, and most likely it's because of our maybe sensor system is much better. But again, I'm just listing this here to sort of to capture your imagination and provoke some thoughts. Okay, so that's pretty much it. Let's just summarize what we learned here. So there has been a significant progress in visual recognition, but still, despite high performance models, are very brittle and perform poorly when the input is perturbed. Image data set was very instrumental for a long while. Now it's been retired, and the situation is sort of unclear how to gauge the progress, and now it seems that most of studies are focused on making the models robust, because the models are already very good at accuracy, and now how to sort of meet both of these criteria seems to be a challenge, because you make the models more robust, you're going to lose some accuracy, okay? Whereas in humans, we have both. Object detection is a very difficult task, as we saw, and there's a big performance gap to meet the empirical upper bound that we calculated. We saw that how you can learn from neuroscience, in particular white noise analysis, to identify the behavior of a system, of a neural network in this case. And regarding the adversarial attacks and defenses, the best defense still is the adversarial training, which is kind of unfortunate, because to me at least it seems that we need some structural novelty to make the models robust, whereas training is just about, again, showing more data to the model. And the fact that the models are actually very brittle sort of hints towards something being fundamentally wrong. Maybe we should go back to the drawing board and just like CapsuleNet, for example, come up with new models, or group convolutional neural networks, right? Which has some intelligence in the structure rather than just the way that we train the models. And okay, so for the future, it looks like there is this sort of a stalemate, or at least maybe a confusion where should we go next. There are some nice ideas, group acquiring convolutional networks and capsule nets, but there's a long way to sort of to go to make the models much better. Okay, the vision is a very, very difficult problem. It's a magical system that we have, does this very accurately and very robustly, yet we don't know much about it. The role of context needs more examination. The way that we calculate upper bound, I think, was nice, and it would be interesting to see the empirical upper bound being calculated for other tasks, in particular instance segmentation. So another advantage of this is actually sort of pinpointing where the models fail and what are the weakest links that have to be basically remedied, right? How to be fixed. And we talked about the texture versus shape hypothesis, and we learned that if you inject more shape bias inside the network, then you can make the network more robust against both regular and common image perturbations, as well as adversarial ones. And also a tighter and more collaborative work and discussions and communication between human research and computer vision research communities would be very, very, very rewarding, I guess, in the long run. And another important point is that the deep models fail in both transformed images like translation, rotation, in plane, out of plane, in plane, in depth rotation, uh, lighting and such, right? At the same time, they're also brittle against adversarial examples. And the main question is this basically, do these models fail because of the same reason on these types of uh, perturbations, or these are different processes, different things, right? The consequence of this being, maybe we can come up with an architecture that sort of can handle both. Okay, if it all this being said, maybe we have a lot of data, a lot of models, a lot of observations, a lot of papers, lots of code, so many things. Right now, maybe it's time to sort of stand back and look at the picture and see what is going on, and basically to fix the problem fundamentally. Okay, thank you very much for listening. I appreciate that, and stay safe. Thank you very much.
Have that much time left, so I start with the questions. If you can hear me, Dr. Borji, are you there? Okay, can you hear me? Okay, let me use the headset. Apparently there is an echoing going on, so okay, is it better now? You're still happy? Okay, so the first question is, in the early part of your presentation, you were talking about the robustness definition. What do you mean of the robustness? Is it the fooling rate, you mean?
Well, the definition of robustness is basically however way that you can make a model fail, and you don't want it to happen, right? That's robustness, right? Now it could be like natural perturbations, like if you simply rotate an image, or you can do it through optimization, or just adding a little bit of basically gradient to the image, right?
Yeah.
And the way that is measured basically drop in accuracy, right?
Okay, basically it's the same as the fooling rate. You just import the perturbation and counting how many of the images are
Exactly.
misclassified.
But there are some subtleties on this. It's a matter of basically debate. There are a bunch of papers, but the good fellow on how to calculate this, right? Which I didn't get into, but yeah, you have to be more careful on that. Yeah.
Okay, so the next question is adversarial. No, this one. Is the adversarial exemplar something that we can get rid of it at all? Because apparently, whatever we do for classification, right? There is some, at the end, there is some boundaries between the classes, right? So no matter what you do at the end, if you add some perturbation, you can just through one sample to the cross the boundary and get to the another class. So it seems that there is no like 100% let's say solution for the defense against the adversarial example. Is it right?
It's hard to say, right? First of all, we have this amazing example, visual system that does this, which basically what it does. Vision is also a computational system, right? And basically we have a living example. And it's possible. The fact that we haven't figured it out yet doesn't mean it doesn't exist, right? So the whole story would be like you make these examples far enough from the boundary such that if you want to sort of go to the other side, you make it perceptible, right? That's the whole thing. Yeah, so
Okay.
it's sort of the fact that we don't know, it doesn't mean it doesn't exist.
All
My
right.
opinion is it actually exists. Yeah.
It's interesting that you said about the imperceptible. I was thinking, is there any measure? Is there any measure for saying that this adversarial example or this, let's say, perturbation lead to an imperceptible or perceptible attack? Right, because right now we're talking about the, let's say, you said about the robustness, right, the fooling rate, right, but we didn't, in the literature there is nothing that showed that, okay, this perturbation lead to a perceptible attack or adversarial example, but this one will lead to a like imperceptible ones, right?
So if you look at the literature, right, it's basically the way that you define these adversarial examples is either by, there are three ways in principle. The first one being minimum distance attack, which means that you want to basically fool the network, but you want to, at the same time, you want to apply the minimum perturbation, right?
Mm-hmm.
Right. The other one is you want to maximize the loss, right? You want to basically, the first one was you you don't care how much you perturb, right?
Mm-hmm.
As long as you can fool the system, right? The second one says that I don't want to apply more than a certain degree of perturbation. In other words, I want to be within a ball,
Mm-hmm.
L2, L0, L1, or L infinity, and at the same time do the fooling rate. But you never want to, you want to always stay in that ball. The third one would be basically a regularization that you sort of add a bit of that, the first one, plus maximizing the loss, and then basically you sort of optimize for this. Right, so this is how you basically control for perceptibility, and it's actually still not very clear how to formulate the perceptibility, and there are some studies on that, but there it's like simply you can think of it as L infinity, for example. You don't want to add more than a certain level to each pixel, or
Yeah,
you just
there's
say yeah, the Euclidean, the L2 of all, for example. Right? There's no real justification why this is good for perceptual understanding of us, but nonetheless people use.
okay. So we have another question. So you are solving the problem using shapes. What if the shapes are perturbed as well?
Yes, great question. So if you go back to that slide, you're probably seeing this visual illusion. There is this lady, and from one angle you can see it basically it's a perceptual organization example, and then from one angle you see it as a young lady, and as another angle you see it as an old lady. But this has been very carefully crafted by an artist, right? So the artist gets these edges, move them around and stuff, right? So the whole point of this shape defense would be basically if you want to manipulate the image, then basically you have to change the boundary. It's possible, but the moment you do that, then the change becomes perceptible. That's the whole idea, right? So basically, which is not easy to do, right? So adversarially, if you want to do that, then you have to be much more sophisticated than just simply doing this, adding a little bit or subtracting from the pixels. That's the whole point. A little bit of structural change make it perceptible, right? That's the key.
Okay.
Defense, basically.
Okay. The next question is: can we use non-superable penalty to obtain non-convex penalty and convex optimization problem?
Sorry, say it again.
I didn't get the question honestly. So let's skip that and let's see the next question. For the paper that you mentioned, adversarial example are useful, right? So basically, you said that you extract the knowledge of the model that is trained based on it, right? So you fit some, let's say, the black images, and you attack on the black images, and you see that what was the And by averaging that, let's say the perturbation on these black images, you see that what was this data set that this model trained based on it. That's really interesting, but it seems that it's really slow. Do you know any? Do you have any thought that how many attacks per image were needed in order to extract the information per?
How many images, not attacks per image, because for each image you just go through the network and create one adversarial example. Maybe your question is how many images you need.
How many images? Yes.
I think it wasn't really that. So the white noise needed a lot in order of like maybe 1 million over MNIST, but this one was pretty efficient actually. It was like probably like around 1,000, 10,000. You quickly see something in those. It's not really that terrible. And if you have GPU and stuff like that, it's actually it's practical. It's not that bad. Yeah.
Okay.
But again, it's not very simple. There are much more sophisticated ways to basically tell whether a network has Trojan attack. This one was very probably simplest, but there are better approaches. I'm not working on that much, but I know there are some works on that.
So I wonder because this topic were about this poison attacks, right? So I wonder in your experiments, how many of the input data set that you trained based on it were basically tampered or let's say Trojan inserted on that then you could extract that from the.
I haven't analyzed that. This one was a simple one. I just basically out of 10 classes, I just did like on 1 classes. I did it targeted and untargeted. I really don't know.
Because this is a simple, not simple. I'm saying simpler solution if this poison, let's say this perturbation, added to all the images of this same as a class, right? Which is not the case for the poisoning attack because.
Well, I mean, if you add it to all samples of 1 class, then or basically a test set that has that class, then you may not get good accuracy. The whole point is that you have to also show the network bunch of images with that patch and bunch of images without that. So sort of then at test time, it acts normally, you know. But if you basically poison all the images that you have, then it's probably easy to spot. Okay, that's the whole point.
All right, great, Dr. Borji. We don't have that much time left.
So one problem I have on some of these slides, I just recorded this in the first shot. Right, there are some problems. I uploaded the new slides. If you can share those. I made a mistake on basically the microstimulation. The effect on the psychophysics curve, it shifts it to the left. I mentioned to the right on that slide.
Okay, so I think that the newest slides will be shared to the attendees. So hopefully, honestly, personally, I learned a lot from your presentation, and hopefully this event will be a start point for more collaboration with all the attendees. And I think your contact information will be shared. So the attendees can just email you for more questions if they have or more collaboration opportunities they're looking for.
Sure, great. Thank you very much again for organizing this and for all the attendees. I hope you guys enjoy the rest of the talks. Thank you very much.
Thank you. Have a great day.
Yeah, thank you. Bye.